Hello and welcome to my 301 CR research submission presentation. I'll begin with a presentation of the application, an example, sorry. So when we run the client side, we load the audio system, it loads us to a main menu state, we connect to the server, and if we click play, we go to the game state. We can move around and send position data from the client side to the server side. The event received, the server then sends that data back, and we can also collide, taking us back to the main menu state. So to start off with the backbone of the application, the engine class, we create a game data struct which houses all the significant subsystems of the engine, and we can access that game data struct with the shared pointer called game data ref, and then we assign that game data ref to underscore data so we can access it throughout the system. The first significant subsystem that we implement is the finite state machine, which manages the different game layers. With the state management, we can neatly organize the code of different stages of the game into its own classes. The different game state classes inherit from this base game state class and implement the virtual functions, and then the main game loop calls these functions. So in the state machine, we simply have the add state, process state, and get active state. This adds state to the stack. This processes the current functions on the initialization of it and pops any states off, and we can get the reference to the top state of the stack. We create a shared pointer, so we have a reference to the stack, which is created here, then a new state with the unique pointer state ref, and then balls for controlling the state machine. And here you can see in action, adding the state, the ball is replacing the set to true since we don't have a pause function, using the semantics of move to move the pointer to the new state we're adding, and then the process state changes, which runs at the beginning of every game loop. We push it onto the stack, and then run the initialization, and then we can return a reference whenever we want to the top state, so we can, well, in the main game loop anyway, return a reference to the top state, so we can run the virtual functions from there. So in the actual engine.cpp, we have the main engine class, which we get to from the entry point. Through the data struct we specified, we can run the window.create feature and create the function, and then you run the state machine add state, and the state we're adding, in this case the main menu state, then run the function below, which is the main game loop. Here we run eNet specific functions, which we'll get to in a bit, and variables for capping the tick rate, which we just basically get the difference between time, the total time, and then limit when the functions run. So here we're getting the current state and then running the handle input update, and same for the draw, and then we just pass in DT for both of them, and then again eNet functions for destroying the client when we're outside the game loop. So the eNet itself, we run the necessary preamble in the connect server, like checking if the library is connected and so on, and the port we're connecting to. Then the listen to server is run inside the game loop, like we mentioned before. It's an event, it's event-based, so whenever we receive a packet, it records that packet and see out the position data, then all the necessary things, deleting the vector off the heap, closing down the client and deinitializing the eNet library, and this is the position data we'll be sending using the data packet variable on the channel, etc. from the character. So these values are passed in from the get position function SFML. For the level editor, these are the necessary preamble for loading in the file name. We can pass in the specific file name we want, so we can technically have multiple different files for level editing. And then the get lower stack property file takes the file ref, which we just get from up above, the stack header we want to read from, and the actual stack property we want to return. And for the audio manager, similar ethos, all the necessary preamble to initialize the system. The pointers to the systems are already initialized in the header, and then setting the format of the low-level system, and then the low-level we can pass in a file name, use the low-level system create sound to get that file name and assign it to the music pointer, and then we can just play the sound. So for the first state, we have the main menu state, which inherits from the state class. We have the constructor, which takes the game data ref from the engine class and a local instance of the game data ref, so we can access all the significant subsystems. So here, as you can see, we're assigning the game data ref to the local instance, so we can access all the subsystems. Here, as you can see, using the object association way of accessing it, we can run the audio initialization and the audio play, and the Loire preamble here, and the actual way of getting the property. And then we have the asset manager, which we'll cover in just a moment. We can specify a name we want to assign to this, the loading, and specify a name and the value which we're getting for the actual directory, which we're getting from the level editor up above. And then we can actually set that texture using the get texture function from the asset manager, which we are calling play button and background respectively, then setting the position. The only event we need to check for is closing, and then if we do click from the input manager, from the input manager, we could just check if the play button is clicked, and if so, we access the state machine and push on to the new state, popping off the old state, and then we just draw everything. And the game state follows the same ethos, all the level editor stuff, data asset management, and then setting the texture. Where is the game state.h? So yeah, just a quick overview, the actual functions that are run, like reference to game data again, the actual background, a clock for measuring spawnings of the asteroids, and then pointers to the object classes, and we can initialize that in the game state so we can actually access these, and then specific variables for the gameplay, and a state-based behavior just to control how the game state runs. So when we start up, it just doesn't instantly run. So in the game.cpp, we actually create new, we initialize we create an access point to these class objects and passing in the data. Then in the actual event manager, check if it's closed, and then from the input manager, we can check what kind of input is pressed. So we've created a clicked up input, takes the SF event up, and then runs these necessary functions from the game objects, and then runs the client eNet client, which we covered here, which sends out the position data of the spaceship. There we go, and this works subsequently exactly the same necessarily for all of them, except for on left, right, up, down, and the eNet send movement packet function to just run and just send the new position data of the spaceship. The update just for the FPS subsystem game object, more or less. It just runs the update FPS in the update, and if the game state is playing, then we can actually move the asteroids, lasers, and then we can actually bring down the asteroids. This is the function from the asteroid class, which actually randomizes and spawns it, all relatively self-explanatory. A vector to check through the asteroid vector, and then we return the spaceship sprite from the spaceship class, and then we can just check if basic collision is detected using the collision object class. We were having a little bug with the laser collision with the asteroids, and so I just chose to comment that out for the time being. Then if game state is over and the death time has gone by, we just run the state machine add state and add the main menu state back on, and then we subsequently draw everything. And just for an example, where is it? Spaceship.h and spaceship.cpp. Anything else significant? FPS and FPS.h. So for the spaceship class, we simply have all the functions we need to run. So state-based as well. So move up, down, left, right, passed in from the input manager, all the necessary variables to actually control the movement of the ship, and again a reference to the game data so we can access different subsystems and the ship sprite. So the ship sprite, we clearly just set the texture that we load up in the game state itself, so we only need to load it once and we can set it multiple times for different entities, setting the position, drawing it, and the actual ship movement. So down below we dictate which state it's in, and depending on which state it's in, it moves in that predetermined cardinal direction. So if we're in move E left, we move down to the left by the dt, minus in the x-axis, sorry, by the times by the dt, and so on. And then we return a reference to the sprite so we can check for collisions or get position data values. And FPS is done is accessed a similar way, so the .h, oh yikes, okay. So game data, local game data reference, so we can assign it, then the draw and update FPS, and then just the general variables we need to work out the FPS maths. So we just get the time difference between the frames, divide that by 1 to get the FPS, then we use the text to string function to get that FPS to a string, so we can assign it. Simple, then we draw it. We're clearly setting a font here, and then the general just attributes of the text itself. So one more time. Moving around, we have disabled collision for the time being, and crashing. Thank you for your time.